Hi, today we're going to talk about functions and relations. So let's look at this. A relation is defined as just a set of ordered pairs. And I've got two examples here. Both of these are relations because there's just sets of ordered pairs. Now a function is a set of ordered pairs that has the additional property that no two ordered pairs have the same first element. So I've got two examples here. And the important thing is, in this one we have 5, 4, 7, and 0. None of those have the same first element, so that's a function. Same thing going on down here. Penny, nickel, dime, quarter. None of those are the same, so that one's a function. If you look back up at these relations, this top relation, notice 1 shows up twice there in the first element. So this one is not a function. This one, though, it is a function because the 4 first elements are all different. So, all functions are relations, but not all relations are functions. Now, this is the formal definition of function. Let's look at a graph of a function. When you think of a function, you probably think more of a graph than a set of ordered pairs. But really, they're the same thing. For example, y equals x squared. I've got that drawn kind of terribly here. Let me try to fix that a little. If I just draw in y equals x squared, it looks kind of like that. That's a function. You can think of this as being every point, any point that we pick on here, say this is 2, 4. This one down here is 0, 0. So this graph really tells us what all of the ordered pairs are. Every point on there is an ordered pair. So we can write that out using this over here, which is called set builder notation. X, y, such that y equals x squared. So we can still consider this as like an infinite number of ordered pairs. And it is a function. Now this down here, this next example, x squared plus y squared equals 4, that's a circle. And this is not a function because if you come over here and you find anywhere you can put a vertical line through it, you can come up with a couple of points that have the same x coordinate, like those two. These two over here might be a better example because we know what their coordinates are. This point and this point this is a circle with radius 2, so this is the point 0, 2, and this down here is the point 0, negative 2. So this is not a function. The one up top is a function. And notice anywhere we draw a vertical line in, where it touches in more than one place, that's enough to tell us that it's not a function. So that's how we get the vertical line test. The vertical line test says that a graph represents a function if and only if no vertical line intersects it in more than one place. So if we go down here and we look at all these different graphs, we can look at them and determine whether they're functions or not. This first one, is that a function? No, because I can draw a vertical line there that touches it in 2 places. Now you might say, what about over here? I could draw this line and it only touches it in 1 place. That's not good enough. If there's anywhere where you can draw a vertical line and it touches it in more than 1 place, it's not a function. Let's look at these others. These next two are piecewise functions. Right here, this function, it's got 2 pieces to it. Notice over here, vertical lines only touch it in 1 place. Same thing over here. Right here in the middle, though, if I draw that through there, it touches the function here. But up here it doesn't touch the function because that's an open circle, meaning that point's not there. So this passes the vertical line test. So is this a function? Yes. Now this next one over here looks very similar, except notice that it's got 2 filled in circles. There's only 1 place here where I can draw a vertical line and it touches in more than 1 place. But that's enough for us to say, no, this is not a function. Now, these next couple of graphs are sparse graphs. They've only got a handful of points. This one over here, the first one, anywhere I draw a vertical line, it's going to touch 1 or 0 points on that graph. So this one is a function. This next one, you can kind of tell right here by the axis. There's a vertical line that touches it in 2 places, so is this a function? No. And this last one, no matter where I draw a vertical line, it only touches in 1 place. So is this a function? Yes. All right. Let's look at some common functions that everybody should be familiar with. In this course, we're going to use graphing calculators or graphing sites on the internet. But there are some certain basic functions that you should just know what they look like. Y equals x squared, you should know is this parabola. Y equals x cubed looks like this. It grows faster than x squared, but the negative half of it goes down. The absolute value of x is shaped like a V. Y equals 1 over x has an asymptote here. And it looks like this. Y equals square root of x looks like this. It's half of a sideways parabola. Let me try that again. It looks like that roughly. And y equals x, of course, is just this line here. So those are some basic functions you should know. Another question we might have is, when does an equation represent a function? And the way you answer that question is, you solve the equation out for y and see if you just get a single value for any x that you plug in. So I've got several examples here. Let's solve each one of these things for y. Now this equation, if I solve it for y, let me change colors. If I solve this for y, I get 4y is 2 minus 3x. Divide everything by 4, I get y equals 2 over 4 minus 3 over 4x. And I would probably rewrite that as y equals negative 3/4 x plus 1/2. So I've solved that out for y. And notice for any value of x that I plug in here, it's only going to give me a single value of y. So is this a function? Yes. That one is a function. Now this next one, x squared plus y squared equals 5. You might look at that and say, oh, that's a circle. It's a circle with a radius of square root of 5. But let's pretend we didn't know that. If you just take this and solve it out for y, you get y squared is 5 minus x squared. And so when you take the square root of both sides, you have to put plus or minus here. And it's this plus or minus that tells us that it's not a function. Because when you plug something in for x, you might get 2 answers out of it. If you plug in x equals 0, that gives me 2 values for y. Plus or minus square root of 5 minus 0. So y would be plus or minus square root of 5. Plus or minus is 2 different values of y. So that's enough to tell us this is not a function. All right, let's look at a couple more. X squared equals y squared. And this is very similar to the one we just did. You get y is equal to plus or minus the square root of x. So this one's not a function. And this one, x equals plus or minus 1 plus y. If I solve that for y, the first thing I'm going to need to do is square both sides. So if I square both sides, I'm going to get x squared is equal to 1 plus y. And if I solve this for y, I get y is x squared minus 1. Now, any value I put in for x here is only going to give me a single value out for y. So is this a function? Yes. This is a function. All right. Let's look at evaluating functions. Now, when you evaluate a function for some value of x, you just replace every occurrence of x in the function with that value. The value being plugged in can be a number, variable, or expression. Now, some of this seems probably very elementary to you. You plug in a number, then it's just plugging it in and doing some computation. But if you can plug in things that are more complicated, let's look at this. If we take this and we do f of 4 is going to be 4 squared plus 3 times 4 plus 1, or minus 1. So that's 16 plus 12 minus 1 is 27. Okay, I imagine everybody came into class knowing how to do that. These other two are slightly more complicated. Actually, this one's easier, f of z. You just replace each x with a z, and you get that. It almost feels like we haven't done anything, but we have plugged z into the function. Now, f of 2x, that one might look a little stranger, but what I'll do is I'll still take f of 2x, and each one of these things up here, I'm going to replace each x with 2x. So first I'm going to replace each x with a pair of parentheses. Then I'm going to put 2x inside of each of those. All right, so 2x squared, you got to square both of them, so you get 4x squared plus 3 times 2x, that's 6x minus 1. So that's my answer there. All right, let's look at this one, evaluating this function at x plus h. When you get into calculus, plugging x plus h into functions is going to happen a lot. So let's do this. F of x plus h is 1 minus parentheses squared, and then we'll put x plus h into those parentheses. Okay, now I've got to multiply this out. Now, if you want to, you could write x plus h times x plus h and FOIL it, but the quickest way to do this is when you're squaring a binomial, square the first term, add twice the product of the two terms, so plus x times h, and then square the last term. And now I'm just going to distribute that negative through there and get 1 minus x squared minus 2xh minus h squared. And that's our answer. Okay, this one is going to work the same way, although it's going to be a little bit more involved because we've got a rational function. So if I do f of x plus h here, I'm going to get 2 times x plus h minus 4 over 4 times x plus h plus 1. Actually, I guess this isn't that much more involved. You've just got to distribute through, and that's pretty much it. So I get 2x plus 2h minus 4 over 4x plus 4h plus 1. And there's not really anything left to do to it. Up top, we could factor out a 2, but there's no real reason to. I'm just going to leave my answer like this. More space on this slide than I really needed for doing that one. All right, that's it for this section.